Okay, day 5. We're going to look at tangent lines again, in a slightly different way this time. They will be mysterious and spooky because it's almost Christmas. First thing we're going to do is we are going to pretend like it was last class, and we are going to find the equation of the tangent line to the curve y equals cosine of x when x equals pi over 4. So two things I want you to know. I want you to round to 3 decimal places. You need to remember that you have to be in radian mode for this to work properly. Now, the first thing we need to do is we need to graph the function. So go ahead and, well, turn your calculator on and then go to y equals, and in y1, go ahead and type cosine of x. So cosine will give you your parenthesis, type x, close your parentheses just for good habit. And now, if you hit the zoom button and option number 7, you will be able to use the Z trig feature, which will give you a nice clean trig window. So when you graph it, it should look something like that. And we want to draw the tangent line at the x value of pi over 4. So see if you can remember how to do it. First thing you do is you need to hit the second button. You need to then hit program, which gives you the draw feature. And you need to choose the option 5 for draw the tangent line. That will take you back to your graph. And now you need to tell it that you want to do this at the x value of pi. So hit second. And then the little caret there, pi gives, that's how you get pi, pi over 4. And again, it'll print x equals pi over 4 right there. And you should hit enter. And then it will graph in your tangent line, which is going to look like that. And more importantly, it will tell you the equation of the tangent line, which is, can you tell I'm typing it in right now? It is y equals negative 0.707 x plus, I lost it, but I think I remember it as plus 1.262. And there you have it. So now see if you can do the same thing here. Graph the function y equals 15e to the point 3t and draw the tangent line when t equals 5. Well, firstly, recognize you can't graph something with t, so you need to graph y equals 15e to the point 3x, and you need to find it when x is equal to 5. But that's a little thingy. So graph this. You're going to need to change your window, but think about what you know from the problem. We're looking at the x value of 5, so we want to look kind of near there, not crazy big. So I'm going to go from 0 to 10, and then I'm going to hit zoom fit to get a good graph. So firstly, make sure you enter this function correctly. So turn on your calculator, go to the y equals screen, and graph 15 e to the. Easiest way to get that is hit second. And then the ln button over here, notice, gives you e to the power of x. So you'll get y1 equals 15. If you're on an old calculator, it'll go, oops, not an a, it will do e caret parenthesis, like that. And you can type 0.3x and close it off. If you're on a smarter calculator, you can get 15 e to the will automatically give you your little like exponent box up there. And you can type in your 0.3x. And you don't need parentheses because you're lucky. But if you're the older one, you do. So go ahead and enter it like that. Change your window again to 0 to 10 for your x values, since we're trying to find the tangent line when t equals 5. And then go to zoom and option number 0 for zoom fit, because that will adjust the y values of the window to the x values that you've specified for this function. So if you did that correctly, you should end up with a function that looks like that, fitting perfectly into your viewing window. And we want to again draw the tangent line when t equals 5. So you need to hit second, draw, which is the program button. Option 5 gives you a tangent, and then you need to tell it the x value of 5. So hit 5 again, it'll do its little x equals 5 thingy, hit enter, and it will print the tangent line equation and draw it in for you. So if you do all that, you should get the equation y equals 20.167x minus 33.612, and it'll draw that tangent line in there. But now I want to show you a new feature of your calculator. So this is the n-derived feature of your calculator to graph the derivative of a function. So we want to graph the derivative of this function y, so y prime, aka dy over dx, aka if f of x equals y, then f prime of x, aka d over dx of 15e to the 0.3 t. That last one is the standard notation you will see that says take the derivative of this function, and on our calculator it will say x equals x down there because we want to graph this derivative. So in order to do so, we are going to go to the y equals screen. Notice now this is where the instructions will differ if you're on an 83 or an 84 with an old OS versus a new 84. In either case, you will have y1 entered into, or you'll have the function entered into y1, and then you need to go down to y2, and you want to call up the n-derive feature of your calculator. So go ahead and make sure your cursor is on the y2 function, and you need to hit the math button, and you need to choose option 8, which says n-derive. It'll print n-deriv on your screen like that. Now you want to go to the vars function button right there. You want to go over to the yvars function, and you want to select y1 because we want to take that y1 function and we want to take the derivative of it. So it'll print that there. Then you need to put a comma, which is right there, a comma, and then you need to tell it to take the derivative with respect to x. So it'll print a x right there. And then finally, after putting another comma, you need to put another x to tell it to do this for all x values. So this is saying take the derivative of the function in y with respect to x at every single x value. Do that, hit enter, it will graph the derivative on the screen. So I'll show you that in a moment. But now if you are on a TI-84, you get to do this in a slightly more convenient fashion. So same thing, make sure you have y1 entered, and then go to the slot for y2. But you have some new features. So you get to hit the alpha button first. Hit the alpha button. So hit the alpha button and then hit F2, aka the window button, and a little pop-up screen will pop up, and you need to choose option 3 for n-derive. Now, when this pops up for you, your calculator will look like this. D over D with a little box, and then a bracket with another like empty box in it, and then x equals another, wait, not that, another empty box. So it should by default put you in the first empty box. In that first empty box, you want to hit the x variable. So just like the other notation, this is saying that we are finding the derivative of the function with respect to x, so it should look like that. And then hit the arrow button to get to this box right here, and you need to tell it what you want to take the derivative of. So you could just type the function in there, But since we already have the function entered into y1, go ahead and use the new features on your calculator to go alpha, and then hit the trace button, which is F4, and that will pop up with all of your y variables. And since we have our function entered into y1, we're going to choose the y1. If you enter it into a different y slot, then you need to put whatever it is. Then hit the arrow button again, and finally, in that last box, tell it x equals x, because we want to take the derivative at all x values. So when you are done, you should end up with one of these two situations. One of those, either the top or the bottom, unless you're on a different calculator, in which case it'll just be like, oh my goodness gracious, I don't even know how to help you. But we are now at the point where we actually want to graph this. So now, if you graph this, you're going to get two functions that pop up. The first thing that's going to happen is the original f of x function that we have there is going to pop up. And if you don't change your window, it's going to be whatever you had as before. And remember, that function looked like that. I had it red on the other screen, but I'm doing it in blue here, because if you have an 84, I think your first one will be blue. So that is going to be your y1 function, 15e to the 0.3x, and then it's ever so slowly going to sketch in the derivative function, which is going to end up looking like that. So that's our y2 function right there, which is the derivative. It will write it as that whole n derive y1 comma x mess. That's what it'll look like. So we now have graphed the derivative of a function that we don't even know how to take the derivative of. So that's nice, because if you hit the up button or the down button on your calculator, you can jump between the two graphs. So you can trace along your derivative function by hitting the trace button, and then you can type in any x value that you want to know the derivative of. So if you type in the x value of, say, 5, you can find the derivative there, and you'll find the y value to be that 20 point whatever it was from the last problem, 20.167. Because think about this, connect the two. We found the derivative at x equals 5, and we found the tangent line at x equals 5, and the slope of the tangent line is going to be the derivative, the value of the derivative at that same x value. So if you go to x equals 5, you will have to get that derivative value of 20.167. And again, that is what this notation up here is talking about. This says take the derivative of the function y at the x value of 5. Then you could type in the x value of 10 to know the derivative at 10. But you have to make sure that you're on the derivative function and not the original function. So you can use this same n-derived feature on the home screen of your calculator without having to graph a function. Totally up to you whether you want to graph it or not, but it's nice to know both ways for sure. So recognize that this limit problem is, again, a derivative in disguise. F of x, the function, is going to be cosine of x. Normally we would say, well, what's f prime of x? But I don't know how to take the derivative of cosine of x. So we need to use our calculator instead. We need to identify the c value of pi over 3. And now we need to put this together and find the derivative of cosine of x at pi over 3, which I'm going to write as d over dx of cosine of x at the x value of pi over 3. Now in class, people were making the mistake of writing cosine of pi over 3. That is a specific number. Cosine of pi over 3 is just a number. So if you try to graph that, find the derivative of that, you're just going to get 0, and you're going to be sad. If you're entering a function, you have to have an x in your function. So we're going to do the same thing as before on our calculator, this time from the home screen. We're going to follow the same set of button pushes as we did on the other page. So go ahead, and if you're on an 83, hit the math button, choose option 8 to get the n derive, and then type in your function, cosine, parentheses of x, parentheses, hit a comma. So there's your comma, there's your cosine function, there's your x variable, comma, x, comma, so hit x again, then hit a comma again. Now this time, instead of doing x, like you did when you graphed it, you need to type in the value of pi, which is second, caret, pi, divided by 3, because we want the derivative of pi over 3. And you should get negative 0.80, what is it, 6? Ooh, 0.866, negative 0.866 right there. If you are on the new operating system, your life is simplified a bit. You need to hit the alpha window button and choose option 3, which is n derive. It'll pop up as d over d blank. You need that blank to be an x. And then you need to type the cosine function in there, cosine of x. And then you need to do the x equals, that equals value needs to be your pi over 3. Boop, 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 boop. And it will tell you the same exact value. So look there at how it needs to be. The bottom is if you're on a TI Inspire CX calculator. And there you have it, using the n drive feature on the home screen of your calculator. So let's now jump back to the tangent line problem. Find the equation of the line tangent to the curve y equals 3x squared at the x value of 2. So remember, we are writing our equation in point-slope form. In order to use point-slope form of a linear equation, you need to know a point and you need to know a slope. So to find the point, you are using the idea that this function, y, 3x squared, is going to look something like that. If you think about this function, we were looking at the tangent line at the x value of 1, 2. So the tangent line is going to look something like that. But huge idea there is that the tangent line and the function both share that one special tangential point, that point of tangency. So we know the x value of the point is 2, so plug that into the function to find the y value. So y equals 3 times 2 squared gives me 12. So I know I have the point 12 lies, I have the point 2, comma, 12. Now I need to find the slope as well. In order to find the slope of the tangent line, I need to take the derivative at that x value. So y prime, power rule says 2 times 3 gives me 6, x to the first. And I need to plug in my y value of 2. So I'm going to get 6 times 2 also happens to be 12. But this is just a pure coincidence. It's not always going to be like that. So y minus y1 is my y value, 12, equals my slope, m, which is also 12 in this case, times x minus 2. Now, again, two key ideas here. The point is on the tangent line and the original equation, and the slope of the tangent line, slope of that tangent line, came from the derivative of the function at that specific x value. These are going to be big ideas for the next problem we do. So now we have this. We are saying find the value of k. St means such that. So find the value of k such that y equals 2x plus 1 is tangent to the curve y equals kx squared minus 3. So we have some unknown k value in the equation of our function. We're given the equation of a tangent line, y equals 2x plus 1, and we want to make sure that it is tangent to this equation there. So I want you to think about this situation in general first. So we've got the tangent line 2x plus 1, which is going to look something like that. And we have some red function, which is kx squared minus 3. Now, I don't care what k is. If you think about what you already know about this function, we know a couple things. We know that the y-intercept of the function is at negative 3 because of that minus 3 right there. If you plugged in the x value of 0, you would get y equals negative 3. So I know that. And that actually tells me something about that k value. Think about this. If I were to draw in this function of a parabola opening upwards, I would cross that line like that. There's no way my parabola could somehow like awkwardly shoot like that to be tangent to it. So I am going to end up with a negative k value no matter what happens, because in order to be tangent to that, I have to be going down like that so that I can smoothly approach that tangent line. I can't cross through it awkwardly like that. So that tells me that k is negative. That's kind of interesting and nice to know. Now here's the deal. We know that that blue line is tangent to this red curve, but I don't know the stretch factor of this parabola, and I don't know the x value where these points are tangent, where these two equations are tangent to each other. So I don't know what this x value is over there. I need to figure that out. I also need to figure out my k value, but I do know the same things that I knew on the previous page. I know that both the red function, the original function, and the blue function, the tangent line, share that green point. That is the point of tangency. That is on both functions. But again, I don't know the coordinates of that point, so I'm going to call them generically A, comma, B. So think about what that means then. We know that this point is on an equation, on these equations. So if you think about that green point being on this blue equation, what that is saying is that if you plug in that x value, which is A, into the blue equation, the y value that you get will be the b value. So you plug in the x value, you get the y value of that point. That's how functions work. That's just what that means. So you can think of this equation right there that we get. Now, that point is also on the red function. So I can say then, if I plug into my red equation that x value, plug in my x value, which is A for x, I will absolutely positively get out my b value for the corresponding y. So notice I've got these two equations here, and what can you say? Hey look, they're both equal to b. Well, if that's equal to b and that's equal to b, then they are absolutely equal to each other. So take one of your expressions for b and substitute that into that other equation. So we can say that k times a squared minus 3, a squared minus 3 right there, we can say that that is 100% equal to that other function, my blue function, which is 2 times a plus 1. So I get that situation right here. And I'm going to leave that unsimplified for now, because think about the other thing we know. We just got a equation based off of what we know about that point A and B, the point of tangent C. We know it's on both functions. Think about the other thing we know when we're writing the equation in, say, point-slope form or slope-intercept form. You know a point and you know a slope. So you got to remember the relationship between the red function and the blue function. The blue function is the tangent line to the red function. The slope of the tangent line, so that slope there of the tangent line 2, is the value of the derivative of the red function at that point of tangency. So if we take the derivative y prime of that red function using the power rule, I will get 2kx, because the derivative of kx squared is 2kx, derivative of negative 3 is 0. So that is my, what am I saying? That is my derivative function right there. And what do we know about the value of the derivative at, say, the x value of a? So 2k of a. Well, I know that the derivative of that point is 100% equivalent to the slope of the tangent line at that point, and the slope of the tangent line at that point is 2. So now I get that equation. And now I have two equations and two unknown values, a and k, so I can solve my system of equations. Look at the new equation we got over here. 2 equals 2ka. I'm going to simplify that to 1 equals k times a. And I'm going to solve this for k. So I'm going to write 1 over a equals k. So now I have an expression for k. I'm going to plug that into this equation over here. K is 1 over a, so I'm going to get 1 over a times a squared minus 3 equals 2a plus 1. Now I have one equation with only one unknown variable, a, in there. So notice I have a squared over a. 1 power is going to cross off with 1 power there. So I'm going to get a minus 3 equals 2a plus 1. Subtract a from both sides, subtract 1 from both sides, you get negative 4 equals a. But again, remember what a is. A is the x value of the tangent point. A is the x value of the tangent point. So I know that this x value is negative 4. And I want to know my k value, so I need to take that a that I just found and plug it in right there. So k has to equal 1 over negative 4. So k is negative 1/4. And so what we're saying is the equation of this red function is y equals negative x squared over 4 minus 3. And you should check yourself on your calculator. You should graph this function, and you should draw the tangent line at the x value of negative 4, and you should get your calculator to tell you y equals 2x plus 1.